Set difference, an overview. The set difference of x and y, also read x minus y, is denoted with the minus symbol, and it is the set consisting of those z from x which satisfies the condition that z is not a member of y. Here is a visualization. In this diagram, the difference of x and y is the shaded area. Here's an example. Consider the set with elements 1 and 2. If we perform the set difference operation with the set containing 2 and 3, this results in the set containing the number 1. Indeed, 1 belongs to the first set, it does not belong to the second set. This is the only element with this property. We are looking for elements which belong to the first set but do not belong to the second set. And the set with 2 and 3 minus the set with 1 and 2. In this case, the only element that belongs to the first set and does not belong to the second set is the number 3. So it belongs to the result. Please notice that although 2 belongs to the first set, it also belongs to the second set. 1 does not belong to the first set, so the result is indeed this. Here is a fact useful in proving properties of sets when the set difference is involved. Z is a member of x minus y if and only if z is a member of x and z is not a member of y. When we negate both sides of this equivalence, we obtain z is not a member of x minus y if and only if z is not a member of x or z is a member of y. Is the following true or false? X minus y equals y minus x. So the question is about commutativity of the set difference operation. This is false. And here is a related proposition. X minus y equals to y minus x if and only if the sets x and y are the same. We'll construct a proof. Please notice that the proposition has a form of an equivalence. This consists of 2 implications. There will be 2 implications to prove. And first, let us notice that the implication from the right to the left is obvious. Well, indeed, if we assume that x equals to y, when we consider this equality, we are free to replace x by y. And this would result in the expression y minus y equals y minus y, which are obviously the same. So we do not need to do anything else about this implication. We'll now prove the implication from the left to the right. So we'll be assuming this equality, and this will become our goal. Please notice that the goal is an equality of sets. 2 sets are equal if the first is a subset of the second and the second is a subset of the first. So we plan our proof as consisting of parts showing these two inclusions. To prove the first inclusion, that X is a subset of Y, we take an arbitrary element U from X, and our goal is to show that U is a member of Y. While our goal is to show that U belongs to Y, let us assume the contrary. And with this, our goal will be to obtain a contradiction. Once we have a contradiction, this will conclude the proof of this inclusion. So, okay, let's take an inventory of our assumptions so far. We are assuming this equality. We are assuming that U is a member of X. And we are assuming that U is not a member of Y. From this and this, we have that U is a member of X minus Y. But now, what do we know about X minus Y? X minus Y is the same as Y minus X. So, U is a member of Y minus X. And if so, it is a member of the first set and not the member of the second. But being the member of the first set means that it is a member of Y. We obtain that U is a member of Y. This contradicts our assumption that it was not a member. We have a contradiction. This contradiction concludes the proof of this inclusion. For the second inclusion, I will just state that it holds by symmetry. Please notice that in our assumption and the goal, X and Y play symmetrical roles. If we rewrite these equalities in such a way that X gets replaced by Y and at the same time Y gets replaced by X, there is really no change in what we are assuming and what the goal is. Maybe we need also to exchange the left-hand side and right-hand side of the equality, but that's not an essential change. So the assumption and the goal are symmetrical with respect to X and Y. Once we proved one inclusion, the other could be proved in exactly the same way, repeating what we said before, but making the change in which X becomes Y and Y becomes X at the same time. So this ends the proof of the proposition. Some exercises. Prove these equalities. The reasoning will be similar to that which we went over in the previous proposition. Complete the following. What are the values of expressions involving a set, empty set, universal, the universe of discourse U, and also some cases with complements. Making diagrams may help in answering these questions. And somewhat more challenging exercise. Complete the following. X is a subset of y if and only if x minus y is equal. Again, make a diagram, and this would help you with finding the answers.